Greetings. This is a presentation wherein we will be discussing about design and implementation of a sliding mode controller for canonical switching cell converter for electric vehicles. In here, so this particular slide gives the abstract of the project. In this project, we are designing a sliding mode controller for high performance DC-DC converter used to drive a brushless DC motor. And the reason for specifying it as a high performance DC-DC converter is that we have done a literature survey wherein the buck boost converter, SEPIC converter, CUC converter, and the list goes on. Comparing all these converters, we found that this canonical switching cell converter, which is one of the latest configuration, offers better performance. The converter performance and controllability is better when compared to the earlier converters. And similarly, the converters, most of the converters used PID controllers as the prime controlling element to enable the switching of the circuit or controlling the speed of the motor which is used. So PID controller used to be the predominant one in many applications, and even in many industries they are using this. Now the advancement in technology, all the VLSI integrations and computing technologies now available nowadays, it is possible for us to implement all other forms of converters, controllers as well. Other forms in the sense MRAS, PDC, and sliding mode. These are all some advanced methodologies in which we will be able to control your converter output or the speed output of the device which we use. Hence, we preferred to go with sliding mode controller for controlling this DC motor. And the same has been given here. In this, we are using a brushless DC motor, which is one of the common motor that is used for electric vehicles. Moreover, in this presentation, we have given a generic outcome of this particular converter and controller, because we will go when we go for the application part, we will see what are all the different areas where these converters and this control technology can be implemented, and in that electric vehicles are predominant. I agree with that. And moreover, first, to analyze whether this is suitable or whether this will work out, we just did a Simulink model. And with all the parameters of the brushless DC motor, we simulated the entire model and we just checked whether it is capable of giving a performance whichever is desired. So we will say that in that approach we got success, and hence we went for a prototype, and we felt that the prototype is also working good. It gives a very similar performance to the Simulink model. In here, we can see all the introduction of what is the sliding mode control, what is this approach is all about, and about a brief about the canonical switching as well. And these slides gives the literature survey which we have done, comparing all the different controllers whichever are there in the modern days. The very latest papers you can see here, we have took papers from 14 till 17 we have taken papers, and we compared all those things, and we felt that this would be a better choice. Even there have been proposals from the same area, we felt that this will be better, and we just implemented, we tried to implement it the same, and we found we got a success in that. So this is the literature survey about that. This gives the block diagram. In here we use a bridgeless converter model. The left hand side is our single phase supply input, and then that is directly converted into DC through the canonical switching cell converter, and that is fed to the VSI VSI fed VLDC motor. And based on the outcome, the motor is closed loop control is done in the motor using the electronic commutation with respect to the positioning of the Hall effect sensors, and the speed of the motor, DC link voltage of the converters are taken as a reference, and from there we are generating the PWMs, that is the pulse width modulating signals for your thyristors that are to be used. In here we have used MOSFET devices which are good in handling voltages as well as high frequency switching. So the speed of the machine can also be easily controlled by changing the switching of it, and the Here you can see the diagram shows a PI voltage controller for the voltage, wherein we have enhanced it with a SMC as well. Fine. So here, this is the existing systems, whatever I told about the PID and controllers. They have different controllers, PID controllers, and we use some genetic algorithm or ACO, PSO. A lot of optimization algorithms are there. People used these optimization algorithms to determine the exact value of KP, KI, KD, which are the gains of the PID controller, and then they move forward comparing all those things. In here, what we did is that we just go with the sliding mode controller, which is one of the robust control technology, a technique, a robust control technique, and the range in which the speed variation or the control variation is very, very, what to say, precise. So we will have a very accurate value when compared to all other controllers. This is what has been given in detail in the proposed system. And this is a canonical switching cell converter. This is a single cell converter, conventional one. You can see here, in here we have only one switch for your converting your applied AC into DC with a bridge. We have a DBR, wherein from there we will be able to switch this DC to DC conversion. And followed by that, we have the working of your DC-DC converter. That is our canonical switching cell converter. For the positive half cycle, we have different modes. Totally 3 modes of operation are there for your positive modes, and in the negative mode also. The sense positive half cycle and negative half cycle is what they call as mode, positive mode and negative mode. The diagram gives the working of the canonical switching cell converter for your reference, and this details about the capacitance and inductance values. This is the simulation diagram which we this is diagram, or this is the simulation which we have developed. And in here, this is our sliding mode controller which we have developed using simulation. And this is the voltage, output voltage what we got, and we felt that it is very standard. We got somewhere around 120 volts for what we designed for the design controller. And thing is that there is no limit for the conversion. It depends upon the application, whichever according to the application we can decide the output voltage. Even if you want 10 volts, we can get 10 volts, or if you want 200 volts, we can get 200 volts. And that all depends upon the values that we use in the circuit, whether all the LC values determine all these output voltage levels and the current levels. In here, this is the model which we have developed, hardware model which we have developed for the purpose. And this is the different applications where the developed model, what we have developed, can be implemented. The foremost thing is the electrical vehicles and switching mode power supply systems, and in electrical machines as speed controllers, battery chargers, DC voltage boosters. And these are the applications, these are the places where we can use the prototype what we have developed. And from this application list, it is very evident that if you see all these things, battery chargers, voltage boosters, and speed controllers, switch mode power supplies, and electric vehicles. So when it comes for electric vehicle, the prime motor can be controlled directly. And apart from that, all other equipments which are used in the electric vehicles, for that purpose also, we can use the same application, because the same converter has the capability of working as a SMPS. So we can have the minimized model of the same, which can be used as SMPS. And similarly, we can use another circuitry with this the same model. We can have one more model, and that can be used as your battery chargers. And whenever there is low voltage in the batteries, we can use them as voltage boosters. So there are a lot of what to say ways in which we can use this particular converter and their control methodology to implement in an electric vehicle. So we prefer that this would be a common solution for all the requirements of an electric vehicle. Thank you. Thank you very much.